Hello again from Digicool Things. In the previous video, part 1, I covered the background history of the original 1979 published Dream 6800, which inspired my 689 based Dream recreation project. I then covered the design of my keypad, sound and tape interface module, which I created to provide the I/O for my Dream recreation. Noting also that the interface module could also form the basis of any other early retro project that requires a Hex Keypad and a tape interface. Next, I went through the interface board assembly sequence that I used. Then I demonstrated testing and also the alignment of this new interface board. Finally, teaming it up with my existing Hex Keypad 4x5 matrix with some custom function key keycaps to create an all-in-one keypad sound tape interface module. This finished module was then plugged into the PIA port of my MECB Motorola I card. Together with my MECB OLED display 128x64 card and my 6809 CPU card, we were then all ready to fire up my new Dream 6809 based recreation. So now that I have it all assembled on my desktop, together with plugging in a good old-fashioned portable tape deck and also setting up a camera to capture the display that I'm looking at, we're ready to power up. So, for this part 2, I'll go through the use of the system, covering the Chipos operating system and also the Chip 8 interpreter that it includes. Then we can take a look at my 6809 based original Chipos code conversion that drives the recreation. After this, we can look at the process of entering and running Chip 8 programs. In addition, the process of saving and loading these entered programs from tape. Finally, we'll take a look at the 6809 conversion of the original Dream Invaders 6800 machine code game, which was originally written by the Dream 6800 creator Michael J. Bauer. I have faithfully converted the original Dream Invaders game to now run on my 6809 and OLED display based Dream 6809 recreation. So, we'll probably finish up with a quick game of Dream Invaders 09. Hopefully, this part 2 will give you a good overview of what it was like back in 1979, when many of us had our first hands-on experience with a microprocessor via the Dream 6800. This recreation allows you to faithfully relive the early days experience of using a standalone 8-bit microprocessor system with a hexadecimal keypad, chunky graphics, and a tape interface for saving your creations. If you're too young for this nostalgia, then this recreation also provides a very realistic experience if you want to know what it was like in the early home computing days, a time when the use of early hardware like this was limited only by your imagination and your creativity. Just before I apply power, I'll also point out that trying to film an OLED display with a video camera requires some compromise. I needed to set the exposure on the video camera to try and minimize the image flicker that the camera was creating, while also minimizing the persistence created by the longer exposure. Please just be aware that first-hand to the human eye, there is absolutely no visible flicker, and the digital OLED display looks awesomely sharp, rock solid, and pixel perfect. Okay, with that understood, let's power up. You'll note the power on display of the Dream is quite simplistic. It simply displays a 64K address in hexadecimal which is stored in an internal address buffer. Now, one first-hand observation is that the display actually looks a lot better than it did in 1979. Firstly, we have a nice sharp digital OLED display, but also when powering up our 689 based recreation, I have defaulted the display mode to use the new higher resolution 128 by 64 display mode, together with the new higher resolution 6 by 10 font. The original Dream 6800 had only a 64 by 32 chunky graphics display and used a very basic and chunky 3 by 5 pixel font. We'll change to that lower resolution mode in a little while, so you'll see what it was like. Okay, so entering a sequence of 4 hex digits will replace the currently displayed address with a new address. So 0123. Note that each key entry is accompanied with an audible bleep for feedback. I've adjusted the sound volume via the volume trim pot, which is on the interface module just below the keypad to the right, so it can range from very loud to barely audible to suit your preference. Now, along the top of the keypad we have the 4 function keys. As labelled, the first function enters memory modify mode. Pressing Mmod displays the byte that is located at the displayed address. As you can see, we have 55. You then either enter the 2 hex characters of a byte that you want to replace the displayed byte with, or you press the Mmod key once again to skip to the next address. You can also press any of the other function keys to exit the Mmod mode, returning to just the address display again. If you enter 2 hex characters to update the byte at the indicated address, the new byte is stored and the address auto-increments to the next address. In this way, you're able to directly type in a sequence of bytes to fill a sequence of locations in memory. Okay, so with this understood, there are a few key locations in memory that you'll want to know to get started. Firstly, there are locations as 0002 and 0003, and also 0004 and 0005. These 4 consecutive memory locations hold the start address and the end address +1 for tape load and dump operations. It was generally the common practice to round up the memory range being loaded or dumped to the nearest 256 bytes. So, for example, a small program located from memory address 0200 might, for simplicity, specify a load or dump address range of 0200 to 0300. Speaking of which, 0200 is the typical start location for user programs. It's also the start location for any Chip 8 programs executed by the internal Chip 8 interpreter. The internal Chip 8 interpreter is located from ROM address C800. So, to run a Chip 8 program, you would enter it or load it starting from address 0200. If entering it, you could also then save it to tape, that is, dump it to tape. So, this covers the load and the dump function keys. Then, when you are ready to run your Chip 8 program, you run the Chip 8 interpreter at address C800. Likewise, if you were loading or perhaps manually entering a hand-assembled machine code program, you'd enter the address that you wanted to execute from. Then, with the required run address entered and displayed, you just press the Go function key to jump to the displayed address. After running a program via the Go key, you can return control to Chipos once again by pressing your system reset, in this case located on my CPU card. Now, the other memory location you may also like to know about is 001C. 001C holds the new OLED resolution value, which is 01 for the 128 by 64 high-res mode and 02 for the original 64 by 32 chunky graphics mode. So if I now enter 001C and press Memmod, you'll see that the current boot value is 01. If I now key in 02, you'll note we switch to the original 64 by 32 graphics mode. Let's try that. Straight away, you can see the font has changed to the original ultra chunky 3x5 pixel font. The displayed font provides a simple indication of which display mode we are currently in. So now let's take a quick look at the Chip 8 language. Chip 8 provides a simple yet powerful byte language that provides all that you need for creating chunky graphics games. Each Chip 8 command is 2 bytes long, so 4 hex characters. There are around 32 Chip 8 commands, all summarised in this table reproduced from the first Electronics Australia article in 1979 for the original Dream 6800. You may notice that there are 33 commands listed. That is because the stop command F000 is not actually a command at all. When the Chip 8 interpreter hits an invalid Chip 8 command, it simply exits back to Chipos. Hence, we can consistently use F000 as a non-valid Chip 8 command to exit the interpreter back to Chipos. I'll let you read the Chip 8 commands to get the feel for what's available. But basically, you have 16 byte-sized variables, 0 through F, of which F is a special flag variable. It's used, for example, to detect pixel overlap collisions for your gaming applications. In addition, you have a 12-bit address pointer called I. You can even expand the number of variables by swapping out variables to memory using the memory pointer. The memory address pointer is 12 bits, as Chip 8 is limited to 4K of memory space. But with Chip 8, you can certainly do a lot in just 4K. And of course, you probably don't want to key in more than a 4K program, as it's over 8,000 hex characters. But this is how we created programs in 1979. In addition, if we wanted to write a machine language program or a machine language subroutine for a Chip 8 program, we'd have to hand assemble it, learning all of the microprocessor hex opcodes off by heart. Those were indeed the days. As I said earlier, this dream recreation allows you to realistically experience, or re-experience, just what we had and did back in the early microprocessor days of the late 1970s. Now, to round out this quick Chip 8 introduction, I'll mention that I've added one new Chip 8 command. It is FX95, which enables us to very easily change the OLED display resolution from inside a Chip 8 program. Simply replace the X with either 1 for the power on default 128 by 64 resolution, or 2 for the original 64 by 32 resolution. So, with Chip 8 introduced, I'll now take a quick look at the Chipos 6809 conversion source code for my 6809 recreation. Here is my commented header of the Chipos 6809 assembly source, where I give a brief overview of the changes that I've made. First is a summary of the hardware that this is designed to run on. Then, the removal of the PIA's CA1 trigger for a keypad key press requires a rework of the keypad scanning code, as did the implementation of the 5th matrix row for 4 new function keys. Also, I utilised the new added function keys to enable a new way of exiting the memory modify memod mode. This is via the press of any other function key as opposed to the original requirement to use the system reset. In addition, I changed the user notification of tape dump and load progress to display the start address and then displaying the end address on completion. On the original Dream 6800, tape dump and load progress was signalled by turning off the display, that is, disabling DMA, during tape operations. This was actually required for timing reasons. Whereas, with our new OLED display, no DMA microprocessor interruption is necessary. So we can use this tidier method for dump load completion notification. Next, the entire memory mapped graphic display was replaced with drivers for the OLED panel display. A small note here is that the use of a parallel 8-bit display panel was critical, as only the parallel interfaced panels allowed the reading of the internal display buffer contents. Serial attached panels only allow the writing of display data, therefore would require an external memory buffer to be maintained, as Chip 8 implements an exclusive OR pixel display function. In addition, I implemented a new higher resolution font alternative to take advantage of the new high-res 128x64 display mode, effectively adding a smoother 6x10 font to the existing chunky 3x5 font. It's worth also noting here that Mike was originally limited to the 1K ROM space of the original 2708 EEPROM, which held his Chipos operating system. Therefore, Mike was forced to improvise to get the full code to fit in the 1024 bytes available. He had to get creative and also accept a few limitations in order for the code to fit within the available 1K ROM space. One aspect of this creativity was that Mike implemented a compressed font, which in combination with an efficient decompress routine saved on ROM space. I no longer needed this type of ROM space saving, so I instead went for a more straightforward, simple font image table. Fortunately, the 1K ROM space limitation is now a thing of the past, and we can be more focused on function instead of available space. To support both 64x32 or 128x64 display modes from within a Chip 8 program, I added an additional Chip 8 instruction that allows setting the display mode, either the original 64x32 or the higher resolution 128x64. As you'll note from the header comments, I also changed the original C000 Chip 8 interpreter address to now be C800. For Chip 8, I found C800 seemed to be more intuitive. Next, the originally published Chipos subroutines have all been relocated to a fixed address redirect table, starting from F700. In addition, there was some refactoring of code and removal of features no longer necessary. Apart from all this, a number of small changes were made along the way related to the new 6809-based hardware. Finally, I've noted in the header that the source file comments that are in uppercase are the original source comments by Michael Bauer. My added code comments, or comments for my amended code, are all in mixed case. Here's an example of this around the delay routine, where original code and comments are in uppercase, but my amendments are commented in mixed case. So, with all that explained, I'm going to start by keying in the first example Chip 8 program that appeared in the second Electronics Australia article. Here it is. This was a simple, short program to display random dots on the display. This achieved a few things. Firstly, it demonstrates how simple and capable a short Chip 8 program can be. Secondly, it demonstrates the exclusive OR functionality built into Chip 8 graphics display. That is, a dot drawn on top of an existing dot erases it. Finally, it also demonstrates the pseudo number sequence of the random number generator. All dots will eventually be drawn, then erased due to the pixel exclusive OR function. So, noting we are still currently in the original 64x32 mode, let's get that keyed in, starting from address 0200. CA3F, CB1F, A20A, DAB1, 1200, 8000, and MECB. With that keyed in, let's now run it by entering address C800 for the Chip 8 interpreter and pressing go. There we have it, our first Chip 8 program entered and running. You may or may not be able to imagine just how that felt back in 1979 as our first program running experience, back in the days when we didn't have computers or the internet. It may be difficult for younger folk to comprehend this, but for those of us who experienced it firsthand back in 1979, it was a truly magical and a future life-defining experience. Okay, with that done, let's try the tape interface. I'll hit reset. One thing about keying in a program is that once it was running correctly, you wanted to save it to tape, so you wouldn't have to key it all in again after powering off the system. So, as explained earlier, I'm going to first enter the dump address range 0200 to 0300 from location 0002. MECB 0200 to 0300. Having done that, I can now make a note of my tape position counter, which is about 50, then press the tape record button. After a few seconds, to allow a leader tone to record on the tape, I then hit the dump function. On the display, you'll note the start address 0200. On dump completion, the end address 0300 is now displayed. This signals I can now stop the recorder and make note of the end counter address. As mentioned earlier, on the original Dream 6800, the DMA-driven display was turned off during tape communication for timing reasons. So the return of the display would signal the tape operation had finished. So on our 6809 OLED display recreation, we instead use the displayed address to signal the status. At this point, it's probably also worthwhile showing you my spreadsheet format I used for noting my tape program saves. Here it is. You see, back in 1979, we didn't have things like an automatic directory of saved programs. All we had was the tape counter. So we'd normally make a note of the tape counter positions for each tape used to build a handwritten record of our saved programs. Remember, we didn't have computers back then. As you'll also note, the new Dream Invaders 09 program, which I've also saved, also includes a verify routine, which we can run to calculate a checksum, in this case stored at memory location 00FF. This verify routine enables us to verify that a tape load was likely successful. Okay, so with the tape dump of our first entered program completed, let's test it by first turning off our dream recreation, thereby losing the entered program, and turn it back on. Now, if I check the bytes at address 0200, you can see our program is gone, but hopefully not lost. So again, I'll set up the tape load start and end locations of 0200 to 0300. So as you saw, I entered the address 0002, then I hit the memory modify function key, and then I entered 02000300. So next, I'll rewind the tape to my saved tape counter location. Press play on the tape and press the load key. As with dumping the program, when the load is completed, the Dream display will update the load end address of 0300. Okay, so I can stop the tape. And let's look at the memory location 0200 again. And once again, we can see the program in memory. So let's run it again to confirm. So I'll enter the chip 8 address of C800 and press go. And we're up and running again. Now, this time, I didn't change the display mode back to 64 by 32. And we also haven't added the new display mode setting chip 8 instruction to the original program. So what you can now see is the original program, but running in the top left corner of the higher resolution 128 by 64 screen. So now is a good time to show how simple it is to modify the program to now work in the higher resolution 128 by 64 mode. So I'll hit reset. And if we step through the program from 0200, we see the X coordinate is in variable A and it's being set to 3F, which is equal to 64 in decimal. So if we change that to 7F, which is 128, we'll have the wider 128 X coordinate range. So let's key 7F. Likewise, at 0203, we have 1F, which we want to change to 3F. So we go from 32 vertical rows to 64. Now we exit memod mode by pressing any other function key, and we rerun the program with C800 go. And we now have a high-res 128 by 64 random dot display. We could of course choose to now save this to tape, but instead I'm going to enter a new program. So I'll go reset again. Now this program creates a countdown timer from 250. This featured in the 4th 1979 article on the Dream 6800. This is the original article. So let's get it all keyed in, starting from 0200. Now, note that we are in high-res mode, and we haven't added any display mode change command. So when we run this 64 by 32 resolution program, we mightn't get the expected result. Let's see. Address C800 for chip 8 and go. Right, we can hear that we have a countdown timer with a beep every second, but the display is a mess. On closer inspection of the program, we can see that the decimal characters being displayed are being truncated and overlapped. That's because the low resolution font is 3 by 5 pixels and our higher resolution font is 6 by 10 pixels. The program is spacing the characters only 4 pixels apart and only displaying the first 5 rows of each character. No wonder we have a mess. To fix this, we simply need to double the number of rows to display to 10 and also double the character spacing to 8 pixels. So let's do that. Reset. So if I go to 022C, which is our display instruction, starting with D4, if I go to the next memory address, we've got 55, which is variable 5 and display 5 rows. So if we want to display 10 rows, I'll change that to 5A, A for 10. Then we have load variable 4 with 04, 7404. So if I change that to 08, it'll double the spacing. Now if we run it, we can see our countdown. We hope. Go. Okay, so finally, let me reset that again. To complete the 128 by 64 adjustment, we could also double the coordinates of the countdown display position so that the countdown display is more centered, just like the original 64 by 32 version intended. So let's do that. At address 0208, we have variable 4 being set to 18 hex, which is the horizontal position. So if we double that, we'll be at 30. So let's go 18 and we'll change that to 30. And then the y coordinate, which is in variable 5, is set to 10 hex. So if we change that to 20 and then exit memod, and let's run it again. Okay, that should by now have given you a good introduction to Chip 8 programming and also modifying existing Chip 8 programs to run with a higher resolution display. Next, I'll mention the Dreamer newsletter. The Dreamer newsletter was published in 19 issues between September 1980 and 1982, providing support and publishing plenty of community-shared programs for the users of the Dream 6800. What was of nostalgic interest to me was that the first computer program that I ever wrote was one I wrote in Chip 8 for the Dream 6800. I called it Dogfight, and it was eventually published in Dreamer number 17 in January 1982. Here's the page from Dreamer with my Dogfight program. Now, to spare you the pain of watching me type this all in, I've already done it, and I've also saved it to tape. Interestingly, it didn't actually work first time. So, to figure out why, I manually disassembled the program, and that brought to my attention a number of machine code subroutine calls. In writing the program way back around 1980, I had made use of the Chip 8 ability to call machine code subroutines. As my Dream 6800 recreation has been implemented on the newer, more powerful 6809 microprocessor, the original machine code instructions were no longer compatible. Firstly, because the 6809 is not fully binary compatible with the 6800. Secondly, the standard Chipos subroutine addresses have changed. To explain further, while converting the original Chipos code from 6800 to 6809 and also modifying the code for the new hardware implementation, the original hardwired call addresses have, of course, changed. To ensure that any further changes to the Chipos code does not again change the published standard routine calling addresses, I took the approach of creating a fixed address jump table for all of the published Chipos subroutines, as explained earlier. This will solve the issue going forward. It's also worth noting that adding a subroutine jump table wasn't possible in the original Chipos implementation, simply due to the limited space in the original 1K ROM, as also explained earlier. In addition, the opcodes of some 6809 instructions have also changed from what they were on the 6800. In some ways, it's actually surprising how many opcodes remain unchanged, even though the instruction mnemonics have changed. For example, an A accumulator immediate load instruction was different on the 6800 compared to the 6809, as shown. Despite this change in assembly code mnemonics, the opcode byte for an immediate data load of the accumulator A is still 86. This is similar for all of the 8-bit accumulator instructions. However, the opcodes for loading the X index register has changed. For example, the immediate data load of the 16-bit X index register was CE on the 6800, but it has changed to 8E on the 6809. So, as explained, in order to solve the initial failure to run the Dogfight program, it just required me to locate the machine code subroutines and amend the appropriate bytes for 6809 machine code instead of the old 6800 machine code. Here is an example of one of the identified machine code subroutines, and in the right-hand column are the byte changes needed to correct the program to run on the 6809. With a total of 4 machine code subroutines located and all amended for the equivalent 6809 opcodes, my Dogfight game was finally up and running. So, now let's look at a bigger challenge. Having first played with and proved that Chip 8 was functioning as expected on my Dream 6809 recreation, I decided I'd really love to try converting the original Dream Invaders. Dream Invaders was a 2K 6800 machine code game written by Michael J. Bauer in 1980. It even required the original Dream 6800's 1K of RAM to first be expanded. For example, with an Electronics Australia December 80 published 4K memory expansion board project. This was necessary before you even had the memory space required to load Dream Invaders. So I dived into making this a bonus extra for my Dream 6809 recreation. Here is the header comments for my Dream Invaders 09 conversion. First, I had to locate the source code and then convert it to 6809 code, which was also compatible with my favourite ASM 6809 assembler. Secondly, I had to work through the code to change any Chipos subroutine call addresses, as I'd outlined earlier, to the new jump table addresses. Finally, I had to identify any other code changes that were required to support the hardware changes implemented on my Dream 6809 recreation. And success. I now had Dream Invaders 09 running on my recreation. It's really awesome and nostalgic fun. A future challenge, either for me or somebody else, is to enhance the Dream Invaders to take advantage of the new 128x64 resolution possibilities. I can just imagine the improvement that higher resolution aliens would provide. But for now, I think it's time to finish off this video with a game of Dream Invaders. As I noted earlier, I've had to find a compromise with my video camera's exposure settings to try and minimise the captured flicker with a longer exposure, while also minimising the image persistence of the display caused by the longer exposure. All I can say is that firsthand there is absolutely no flicker or visible persistence while playing graphical games on this display. In fact, the OLED display is awesome and pixel perfect. So, based on my earlier spreadsheet of programs, I had Dream Invaders 09 at counter position 030, and the load address I'll set up 0002 memod. So I want the range 02 and 00 to 0800. So I've positioned the tape at counter 030, which is what my spreadsheet of saved programs shows me. And the load address of 0200 to 0800 I've inserted at 002, 0200, 0800. So I just need to hit play and press load. And we'll see 0200 start address appear on the display. So we just need to wait for 0800 to be displayed to indicate it's fully loaded. Right, there we have it. So I press stop. Now we can optionally run the verify routine, which we don't need to do, but it's a good exercise. So if I start off by having a look at 00FF, it's currently got F9. So I'll exit out of there and I'll go to the verify routine, which is at 07C0, and let's run it by pressing go. And again, let's look at 00FF. And we have 91, which the spreadsheet tells us is the right result. So we should be all ready to run Dream Invaders 09. The run address is 0200. Okay, let's go. And I'm hit. 3 to go. Yes. So, if you're interested in creating your own early retro experience, either for reliving your own experience or going early retro for the first time, Then be sure to check out the keyboard, sound and tape interface on my Tindy store, and also the other components of my dream recreation. There are many other Chip 8 programs to explore, and a lot of fun and educational programming challenge to be had, from coding your own Chip 8 creations. You could even have a go at enhancing the Dream Invaders code for higher resolution and more features, using the 689 recreation's added processing power. As usual, you'll find all the resources, including all source code, on my GitHub repository for this project, which you'll find linked in the description. And if you'd like to support me, please do consider looking at the PCBs and kit sets available from my Tindy store. Okay, time to play. That's it. Thanks for watching.